This is the solution video for question 5 from section A of sample test 4 for CSAT. In this question, we're told we've got a piece of paper with side length 1 with negligible thickness, and we're told we fold it recursively. So for the first fold, we fold it along a diagonal of length √2, thus obtaining an isosceles triangle. And then subsequently, we fold along a diagonal of length li, with I from 1, 2, 3, or any positive integer. And that fold, we're told, results in a new triangle which is geometrically similar to the previous one. Given that information, we're asked, if we continued this process indefinitely, what would the sum of the LIs be? So, how are we going to go about this question? Well, we need a diagram. We need to imagine what this looks like. So, here's our original square. We've got sides 1 and 1, and we know our diagonal is length 2, √2, sorry. And we're told that the first fold is along a diagonal of length 2, √2. So that is, we fold along here and fold over this way to generate an isosceles triangle. And so, taking count of what our Li is, our L1 would be √2. So doing this, you can clearly see we end up with a triangle like this, with sides 1, 1 and √2 from the diagonal here, and we've got a right angle here. So good it is isosceles, because these two sides are the same length. And now it gets a tad more difficult, because we need to work out what our fold would be to make a geometrically similar triangle once we fold it. So there's probably one obvious one, which is to try and fold from here to the midpoint of √2, here, and fold over here, and we get a triangle that looks pretty it's going to look pretty similar to the one we've got here. And we can check it's geometrically similar rigorously. So we're going to fold like this. And just to note, the length of this fold will be √2 over 2, because we know the diagonal is √2 and it's halfway along that diagonal. So this is what we'd get after that. So side length 1, √2 over 2, and this will be √2 over 2 because it's half the long diagonal. So is this geometrically similar to this? Well, the answer is yes. So we've got this right angle here, we're notating the orange. So where's our right angle here? Well, it's here, because it's the intersection of two diagonals of a square. So it's going to have a right angle. So that's good. So what about, √2 is our longest side here and 1's our longest side here. So the scale factor is we times by 1 over √2 to get from this length to this length. But if we times 1 by 1 over √2, we get √2 over 2. And similar here. So this is an exact geometric copy of this triangle, but with all the side lengths scaled by 1 over √2. So that's great. So we know, looking at this, what cut we made, or what fold we made, that we'll make the same fold here. So it was from the right angle to the middle of the opposite side. So it'll be this. And we'll fold that way. And what's the length of this? Well, we could work it out using Pythagoras, or we could just use the fact that our length was √2 over 2 here. And we've scaled it by 1 over √2. So it'll be 1 over √2 times √2 over 2, which is a half. And what do we do now? Well, for the next triangle, we don't really have to draw it out, because we know we're just going to get another copy of this, but scaled by 1 over √2 again. And we know our fold length then will be 1 over √2, what we just had. So if we carried on, we'd have 1/2 times 1 over √2. So, and we continue like this. So we're asked to sum up these LIs. So you'll see that if we times by 1 over √2 each time, this looks like a geometric progression. But only from here. So if we look from here, we've got a geometric progression with the first term A being √2 over 2 and the ratio being 1 over √2, which we can sum up. But then we need to remember though, and be careful about this term over here. So why isn't this part of the geometric progression? Well, it sort of makes sense that this value will be a little bit different, because here, or this jump would be slightly different, because here we're folding from the square into the triangle. Here we're folding the triangle to a smaller copy of itself. And so clearly the behaviour moving from this shape to this shape is different from the rest of the process. So this isn't a surprise that this doesn't fit the rest of the pattern. All which remains is for us to work out the sum of the LIs from 1 to infinity. So L1's on its own, so let's do L1 first, so root 2. And then we've got this geometric progression here that we need to sum to infinity. And we know A is root 2 over 2 and R is at 1 over root 2. So we know that the sum to infinity of a geometric progression is given by A over 1 minus R. So we have plus root 2 over 2 over 1 minus 1 over root 2 here. So times numerator and denominator of this by root 2 tidies it up a lot. So we have root 2 plus, because we make this 1, then root 2 minus 1 because we get rid of the fraction in the denominator here, and we just get a tidier possible answer. So we could leave it like this, but preferably we want to make this as simple as possible for the examiner, so we're going to rationalise the denominator here. So that's times the numerator and the denominator by minus 1 minus root 2. So minus 1 minus root 2 times over minus 1 plus root 2 times minus 1 minus root 2. That's root 2, and if we simplify this, we get plus 1, minus 2, so minus 1. So we get minus 1 minus root 2, so plus 1 plus root 2. And we can group the root 2's together and get our final answer of 1 plus 2 root 2 for the sum of LIs.